Coldfusion. And our mission was to take this from the SnowEx IOP Grand Mesa data sets, querying them from the database, the GPR, and LiDAR. Has got a little example of what that looks like, and to use that information to estimate snow density with it. And SWE, and we validate that. So this is the general idea. We had our pretty awesome team here, and there we go. So I kind of already stepped into the slide, but the main objective was to use this database and really start wrangling with it and go through all of those growing pains. But I was most certainly impressed at the speed at which we could get this data and use it. I was really, really stunned at how quickly Seth was able to do that, computationally wise. So once we were able to bring the GPR and the LiDAR data sets together into the same raster pixel, we took what looked like a spiral and turned it into a square roll, if you're with me, and then we were able to calculate the density and validate that. So that's what we're about to show you, our neat results.
So as mentioned by Tate, we focused in the Grand Mesa area as there were 2 flights that were flown collecting LiDAR snow depths. So our 2 main focuses for at least testing this method were February 2nd and February 13th. With that, we needed GPR data, and instead of just using the specific dates, we did just look at what data we had. And so we had January 28th to February 1st. And then for the second set of dates, there was definitely a limitation as GPR data, all that was left, or all that was put on the database at the time was until the 9th. So there's a bit of a gap there. So we were comparing February 13th LiDAR snow depths to February 4th to 9th GPR snow depths, or snow density, to calculate snow density, sorry. And then we also, in all of this, we are going to be looking at the snow pit density and then also the snow depth and the ASO 50-meter SWE product. So all of this was queried from the database. And just an idea, so on the right here, you can see all 3 points. The bigger points are just because that's little swirlies. So it looks, there's a lot of points within there. And so our 2 date times are anything. One is referencing January 28th to February 2nd, while the 2 is referencing February 4th to February 13th. So that works out for the pits as well as the snow depths as well from the Magnaprobes and any other snow collection devices. So to kind of make this a little bit easier to break down and understand for the rest of us, we kind of put together this flowchart diagram like we saw in last presentation. So more or less just illustrating the steps we took to get here and cutting out so much of the nitty-gritty that went into it. But the database, we pulled out the GPR data, that ASO data, the snow pits, the Magnaprobe. The GPR and ASO data went on to that fusion step, as we hear in our name. A bunch of different conversions happened to that data to get it all in the right formats and to be able to compare to each other. And from there, we produced what I'm calling here our fusion table, which was the table of the fused data. The snow pits was its own table of just the densities. Those 2 things came together for the validation and comparative analysis step. And then the output of that is going to be CSV or PKL or some type of file that can then be used for the data visualization steps.
So one of our first steps here was using a tool we learned early on this week, going in and just querying the available dates for ASO. And once we had those from February 2nd and February 13th, we made this data product to kind of visualize what was going on during that time. Tate mentioned there was a storm between those dates. He was out there actually collecting the GPR data, and we were able to make kind of a cool visual here, showing that depth actually decreased across these dates. And somewhat counterintuitively, according to the SWE product, SWE went up. And that might have been because there was snow densification going on, and there were actually more SWE inputs during that period. But it was kind of a nice place for us to imagine what the trends were and how the winter snowpack was evolving. Back to you.
So to start with, when we started pulling things down from the database, the first step we had was really to plot them up and just see what's what and what's where. So what you're looking at here is all of the Magnaprobe data within the bounding box we set that corresponds to the 2 ASO flights we were most interested in on February 1st and February 12th. The colors here are just the snow depths. Probably a little tough to see up on the projector, but more or less kind of looks like in that range of 100 centimeters or so, a little bit above and below that.
Yeah, so again, just making sure we're able to query the database properly and pull all the data that we want to actually get. So these are 2 plots from the 2 different dates that we're looking at of the snow pit average density. So actually pulling that data, averaging it, and then we'll be using this in our future processing steps. And yeah, just using a lot of the plotting tools that we had given to us.
And so from there, once we decided what days we were focusing on, so we had the GPR data. So with the travel time, we wanted to calculate, well, derive density. So what we used was the LiDAR snow depth. So once we were done the GPR LiDAR fusion, came into this step, and then we used the GPR two-way travel time. So pretty much working backwards in terms of how you'd calculate snow depth. We calculated the wave speed, then the dielectric permittivity to then use, here we use the Kovacs equation to calculate density. And so on the right, we can just see the density within our 2 time periods. And we can see that I guess it's not underlaid, but on the right is a lot of a treed area, and then on the left is an area of open area, and we can definitely see differences there. So yeah.
So I guess along those tracks, we were able to calculate the density through that Coldfusion process. We then grabbed the spirals around the snow pits within a 25-meter buffer to compare. So these plots that definitely don't have any straight line that you can put through them are the comparisons between, on the left-hand side, the GPR LiDAR density, and on the right-hand side is the ASO, the snow model density product, compared to 21 snow pits out of a total of 47. So there is, again, not a complete match between where the GPR went and where the snow pits were dug, but about half of that or so. On average, the GPR LiDAR tended to have an overestimation of density compared to the snow pits, about 140 kilograms overestimated on average, and the ASO about 100 kilograms per meter cube, overestimating that density when compared to the snow pits. So I guess if we look at the maximum values there, there's definitely a bit of outlier removal and some more spatial filtering that we'd have to do to the GPR LiDAR product to get those numbers a little bit more in the realm of reality. This is the comparison just between the snow model density, which we back calculated that from the LiDAR snow depths, and the LiDAR SWE product from ASO. So there's, again, that's taking a 50-meter product down to a 3-meter product. So there's a little bit of spatial smooshing around that we had to do to accomplish that. And then, so that's on the y-axis. On the x-axis is the GPR, the Coldfusion. And really, I guess the takeaway from this is that bringing that GPR into the picture shows us quite a bit more spatial variability, where we have observing a larger range in possible densities than are predicted in the model, even though like the RMSE is pretty large, and again, the correlation is pretty much 0. This tool gives us a little bit more sensitivity to what might be happening to help validate a model like this.
And then just using that derived density, we then just calculated SWE. So we used, again, the LiDAR snow product on a 3-meter resolution with the LiDAR GPR fusion densities that were derived to calculate SWE, which again is pictured here and has similar patterns as we saw in the density graphs as well.
Yeah, so when comparing these two ways of calculating SWE, we saw that the spread of our data supports our hypothesis that the GPR is going to capture more heterogeneous density across the landscape that we'd expect to see. Like Tate mentioned, there does need to be some outlier removals that you can see here. But in general, that interquartile range shows for both these dates how much more diverse the densities from this fusion SWE were. And as we'll see in the next slide here, looking at this first date, the interquartile range from our fusion SWE was significantly higher than that ASO SWE from the 50-meter grid cells.
Yeah, so after we did some initial scatter plots of the SWE values from the last slide, we were wondering about the spatial variability. So we converted those into rasters and compared them against the ASO SWE rasters. And we can see here from the two different date ranges, early February, we've got much lower values for the ASO SWE than the GPR over in the western areas where there's a lot of open meadows. And then for the second flight and the later GPR samples, we were seeing this discrepancy in the southeast corner. So that's something we'd like to investigate further.
And this is just showing the Magnaprobe depths from the database compared to those ASO depths and showing that there's a good relationship there. These depths, I have to imagine, were used to validate the ASO LiDAR. So that went into their data product. But it was a nice step for us to take just to check that and have one more validating mechanism.
Hello. So part of doing these projects is making sure that we can communicate our work and make it reproducible for other people. So I've been working on a README markdown file that kind of illustrates what we've been doing, gives some context to the project, and how the tool might be used later on.
So we'll conclude, that's a good remark from Corey there, that as we continue to work with this type of project that, we're really clear with what we're trying to accomplish, and we also want to know what future steps are next. So cleaning up that data, making it a little bit more user-friendly is a big one. We weren't able to accomplish like the predictive modeling that we could do to distribute densities, which is on the list of to do, and as well as taking this and using this database, which is super powerful, and taking this to other sites, pulling more LiDAR and GPR data from it to investigate other areas beyond Grand Mesa. So with that, I think we'll all just like to thank you for this opportunity, as like stressful and fun as it was all at the same time. So awesome job, everyone. Thanks so much.
Great job. Progress. Any questions from the audience?
Like that.
Any thoughts about, other than just spatial variability, why your density from the GPR Coldfusion LiDAR has such a bigger spread than ASO? Well, where is ASO getting their density from?
So the question is, what might, other than spatial variability, cause such a large range in the GPR estimated densities than the SNO model product that ASO is using for density to calculate SWE? I think that there's a lot of SNO processes that might be happening on a smaller scale than what the SNO model is able to capture. To say that as simply as I can. I don't know the nuts and bolts behind SNO model, but certainly wind redistribution is one of these things. And I think some of that has to do with also comparing these GPR transects that are maybe stretching that time span between LiDAR flights and GPR flight or collections is another thing that could be introducing some biases or straining that density observation.
Good job. So I think we'll do one more and then we'll have a break. So next up is.
Good job, everyone.
Nice job, guys.